All right, hey everyone, welcome back to another week of hobby kernel development. This is week 29. Thanks for joining, and I'm also celebrating 3,000 subscribers, so thanks very much. This week we are continuing with exercise 4 from lab 3 from the MIT class with interrupts. And we made pretty good progress. Yo, what's up, Clatflare? What's up, Nbill? Oh, Nico. I'm gonna do test 2 and make sure the chat is working. Also kick off my my break timer. All right, oops. That's not what I wanted. All right. Yeah, so we're working on lab 3, continuing with that. And today we are going to continue with the rest of the interrupts that I didn't finish last time. Yeah, here's the link, Nbill. Yeah, it's a pretty good one. Let me know if you follow it also. So last time I got the division by 0 interrupt handler or exception handler working, and like mostly working. So we're just going to continue with that today. So I'm just going to get right back into it and just going to actually just retest kind of the previous state we were in last time. So we're going to build and debug it and enter the debugger, and I'm just going to break on divide error, I suppose. And what is the difference between a trap and interrupt that one can nest interrupts and second can't? Hey, I'm not totally sure. I think the terminology is like used very loosely between a lot of these things. I think a trap is just kind of a very general word. But yeah, trap and interrupt. I guess interrupts are, so what I know about this is that interrupts are, strictly speaking, generally more from externally generated by the CPU, like from hardware devices or stuff like this, whereas traps tend to be a little bit more internally generated. And this influences like the interrupt flag and stuff like this. But to be honest, I don't actually know too much about that, but maybe we'll figure it out this time. And Bill asks, how accessible is it? I would say it's medium level accessible. I would say the class is not for beginners. So you should have a pretty, like a decent background already in, I would say, like definitely user space programming and probably a bit of C too. Nice. So yeah, so what I'm gonna do now is I'm gonna go to the div by 0 and I just wanted to find the idiv. Okay, wait a sec, I think I maybe slightly messed something up from last time. I don't know, it looks like it should still be there actually, so let me quit that actually. I'm just gonna make one more time. Just trying to reproduce the state from last week. Okay, that's super weird. Why isn't it there actually? Let me... So what's going on? Wait a sec, so this is the div 0 thing, right? Let me just check my working tree. That seems pretty clean. So oh, maybe I have a guess. It might be due to optimizations. I think I was messing around with this a little bit and messed up the optimization flags actually. C flags, user C flags. Let me try this. I think I needed that last time. It was like 0 on the user C flags. Let me rebuild. Yeah, yeah, there it is. Okay, so okay, that was a bit of a surprise. So yeah, I accidentally got rid of the 0. Yeah, Catholic. Yeah, I just read that the trap gate doesn't disable the interrupt flag in the flags register. Yeah, something like that. That's the detail that I'm not like super clear on, but I think that will be actually pretty important for me to know continuing forward. So, so one last time, let me just get that reloaded in the debugger. And then now I should be able to break on div error, and also I want to specifically break on that program counter. If I continue, good. So now we break on the idiv instruction, and we can do a step. And so step I, so basically what should happen is this idiv is going to trigger a division by 0, which is going to cause the CPU to trigger its division by 0 exception handler, which we have set up. And it's going to divert execution to the handler, which in our code is it's going to be actually in entry trap entry.s. So yeah, so it's declared here in this assembly, in this assembly label. Yo, Afnan, what's up? Hello, white theme, Jesus. Yeah, no longer white theme because of you. I've been fully convinced to go team dark theme for the moment. So yeah. So if we do a step instruction, we hit the divide error, and so that shows that the basic interrupt infrastructure is kind of working. What's up, Zishan? Pretty interested in systems development. What roadmap would you suggest? I'm going to link you to my resources and also this website, pwn.college in particular, which is my personal recommendation for how to get into this stuff. It's from a security point of view, but if you're just interested in low-level stuff, that'll be perfect for you. So yeah, right. So now we're executing in the, is your cam dead or is it my device? I think it's lagging. Let me check. Oh no, camera issues. Yeah, I think I'm having some camera issues. Bummer. Let me see. One second. Yeah, crazy. Let me just try to debug this for 1 second, maybe. I'm using my phone connected. Yeah, all right, I might need to switch to my other camera. No. Oh, hey, maybe it's working now. Is that your phone? Okay. Oh, maybe it was my non-dopamine phone. That might have been it. Yeah. Yeah, this is working now. Yeah, thanks. Yeah, all right, I think we're back. Thanks for the heads up, Afnan. Yeah, it's just my second week trying this new camera setup. So, but anyway. So now we're in the exception handler and we can start stepping through the trap handler. And where we ended last week was getting to this trap function where we handle the exception in C code. We transition to the trap handler in C. And let's just get there. So we can just step through. We can see that we pushed 1 0. So we pushed a first 0 because this particular exception does not produce an error code. So we pushed a 0 just to make sure the struct layout is the same between interrupts that do push an error code and those that don't. Then we push the trap number, which in this case is also 0, and then we jump to all traps. So we do the jump, and then now we're in all traps, which you can see here. And all traps does a couple of things. So the goal is to construct a trap frame, as it's called, which is this structure right here. So we are manually crafting a trap frame on the stack. In practice, we only need to construct kind of these variables at the top of the struct because the CPU automatically pushed a bunch of state that's at the bottom of the struct, like the EIP, the CS, and stuff like this. So we basically pick up where the CPU left off, and so our code actually so the CPU leaves off here. Our code pushes the trap number. And then we pick up there. So we push the DS, the ES, and then all of these registers. And that's what we do here. We push the DS, and it apparently pushes a 32-bit integer already, so we don't need to take care of the padding explicitly. We push the ES, and we do the push AL instruction, which pushes all of the registers in this order. And that's, yeah. And then we do a few things that it told us to. We load the segment descriptor for the kernel, KD, I guess, which is the kernel's data descriptor, into DS and ES. And I actually don't. I see. Yeah, okay. Because we're kind of transitioning into the kernel, I suppose. I'm not totally clear on that part. We move the kernel's segment descriptor for the data segment into DS and ES. And then we simply, we basically want to call this trap function to actually do the trap handling. And that is right here. It's just a function that takes one pointer. And so to call this from assembly, we push the pointer on the stack to pass it as the argument, then we do the call instruction. And let's just observe this working. So push DS, push ES, push AL, move, push L ESP, and call trap. And now this is kind of where we left off last time. So now we're executing in the C code, actually. So we've successfully done the absolute basics of the interrupt handling, and now are able to actually process this in C code. And that's pretty much where we left off. And I think there was a panic. And so that's where we left. So it made it to the trap function, right? I had this panic in here to make sure we don't accidentally execute code that we're not ready to execute. And now let's keep it going. So now we can continue with the assignment. It basically says implement the features described above, which is basically just like all this interrupt stuff. Hi, kernel hack. Hey, yo, what's up, ant guy? Thanks for coming back. Yeah, so we're just, so this is all the stuff I kind of have done last week. But what I have yet to do is implement all the rest of the exceptions. Yo, digitalized. Yeah, new camera angle. Just trying out different things. But yeah, I'm just trying to achieve that really pro streamer kind of look. Yes, it says, test your trap handling code using some of the test programs in the user directory that cause exceptions before making any system calls. You should be able to make grade to succeed. Actually, I'm kind of curious if this whole make grade thing, I've never tried to run these grading scripts. Interesting that I don't have a plain Python. Yeah, it's probably because the scripts are probably Python 2. And on my Mac, I guess I don't have Python 2 installed, so I'm just going to ignore that for now. Yeah, so you should be able to get make grade to succeed on div0, soft int, and bad segment tests at this point. What I actually want to do now is just understand what this code actually does. I haven't really read this C trap handler yet, so let's just do that for a sec. I'm just gonna quickly check the stream quality to make sure it's still good, but hopefully it is. Yeah, Arctan, you have an exam tomorrow? An exam in what? All right, looks pretty good to me. Yeah, so what does it do? So we enter the C code. We have this kind of esoteric thing about the direction flag. I don't really know, I don't understand that. We check that interrupts are disabled. So that's presumably important in the interrupt handler in order to not have to handle an interrupt while we're handling an interrupt. Although I think nested interrupts are supported, so that's something to learn about. If this assertion fails, do not be tempted to fix it by inserting a CLI in the interrupt path. Yeah. Print incoming trap frame, and then if the CS register and 3 equals 3, that is an indication that we trapped from user mode, apparently. So the trap frame is all this data that the CPU pushes. And the CPU, yeah, and we can use that information from the CPU to help determine what actually happened with this interrupt. And so the CPU pushes a bunch of these things, but in particular, it pushes the instruction pointer of the code that was, I believe, executing at the time of the I guess in this case, it's a divide by 0, which is technically an exception. And so I think EIP is going to continue to point at that same IDIV instruction. I believe, not totally sure. And but along with the EIP, it pushes the code segment register, I guess. And using that, you can look at the lower bits of that register to determine what the privilege level of the code executing is. And if it's basically 3, it means user mode. If it's 0, it's kernel mode. Let me check. Oops. Saying, can you make a stream or video on ARM assembly operating system? Yeah, good question. Like I would definitely like to get to that eventually. Probably not super soon because I'm still working on x86 and I probably will be for some time. Yeah. All right, Afnan, see you later. Have fun with the AVR stuff. Yeah, but I'm definitely interested in working on some ARM stuff eventually. Okay, so first thing we check if we're handling an interrupt from user mode. And then if that is the case, then there should be a current environment or basically a process or like task running. And if there is, apparently the environment struct stores the copy of the latest trap frame or something like that. Copy the frame into this so that running the environment will restart at the trap point. Yeah, because when we return back to user space, it does this based off of the to return back to user space, we basically call the same function, this env run thing. But now it's time for a 20-second break. Stretch. Yeah.
Do you need your mic?
No, it's okay. You don't need to worry about being that quiet. Also, doesn't really matter. Yeah. I think it's a little bit like extra character. All right. Yeah. So to return back to user space, we basically just call this function called env run, which is actually what we used to enter user space in the first place. And it basically just takes an environment and executes it using the information in its internally stored trap frame. So that's why it's important to keep that internally stored trap frame up to date. Yeah, so that's what we do. And then apparently we record last trap frame somehow, for some reason. Trap dispatch, so this is actually interesting. So based off of the kind of interrupt, here's presumably where we are actually going to handle them, maybe pretty soon. And you do that using the trap frame. This is print trap frame thing. It says unexpected trap user or process or the kernel has a bug. Interesting. So if the kernel, if it's a trap from the kernel text, from like the kernel, it just immediately panics, which is interesting. We'll probably change that in the future, I would expect, because I think it's pretty normal. Like the kernel definitely has to, I believe, handle interrupts that come from the kernel too. For example, I think like page faults and stuff like this, but I'm not really totally sure. But this is interesting. If it's not unexpected trap, so I'm gonna guess that in our handling code, we need to return. Basically, we don't want to execute this code. Otherwise, we destroy the process. And then the last thing is what? We return to the current environment, which should be running. So we assert that it's there, that it actually is actively running. Interesting, because the environment was by definition running when it triggered the fault or the exception, I guess. And so its scheduler state hasn't changed. So it should be running, and we just run it. So that means if I comment out this panic and actually execute this, which we will see what will happen. What is the theory about what's actually going to happen? So we're going to hit. It's still the same reason. It's still this idiv thing. It's going to go into here. We haven't implemented any code to handle that yet. So we're going to hit the section at the bottom where we basically destroy the process, I think. I might even add a cprintf just to confirm this. Destroying kernel, just so we have a print there. So that's what I kind of think is going to happen. So then if we destroy kernel, which also kind of curious what that even means. Destroyed the only environment. Nothing more to do. What? That is interesting. That is hard-coded to do that. Because it's true, like currently we only have one environment. But that will change that in the future. So interesting that it's hard-coded. So here's, I guess, what's going to happen. We're going to hit the env to destroy. We're going to hit the env free, which does what? Yeah, freeze a bunch of data, I guess. It's going to print this out, and then it's going to go into the kernel monitor, I guess. Let's just see. So I have commented out the panic. Oh, oops. Oh no. I did this weird tmux thing where it like replays all of the characters I type in all of my panes at once. It's like kind of crazy. All right, recompile, and let's just run it. Path3 cannot access memory. Interesting. All right, what happens if I just do this? Yeah, that's pretty much what was expected. So incoming trap at some address. It prints the trap frame, which we can see I guess it's in the trap dispatch, which is not even here. Trap dispatch prints the trap frame, and then goes into here. So do we see the destroying kernel, destroying the only environment, nothing more to do. So that's officially what happens. But it does seem like, yeah, it's just kind of working. So now let's keep it moving and implement the support for maybe some other exceptions or interrupts. And I think it shouldn't be that hard. So now the question is, do we go through them one at a time, or what? Are you developing the kernel from scratch or hacking the Linux kernel? Yeah, this is from scratch, so to speak. This kernel is not Linux. It's a custom kernel, but it's based off of this kind of learning operating system from this MIT class, which is what I'm following. So I didn't start it completely from scratch, but I'm just kind of like working on it and taking it further. But yeah, not related to Linux at all. Let's just, so what are some other things? So soft int, that's another interesting one. Yeah, bad segment at this point. Okay, let's just do soft int. I actually looked a little bit at this previously. And so softint is kind of an interesting user program. What it does is try to trigger the interrupt 14, which is actually, it's actually the page fault interrupt. But it's kind of interesting that a user program is directly trying to trigger this, page fault handler. And the point here is that it's an illegal software interrupt. Like, user space should definitely not be able to trigger this. It's simply not part of the surface area that the kernel exposes to user space. And so it's interesting to see what would happen. And let's just try it out. So softint, yeah. So if I do make key move, so now it actually starts to reboot constantly, which is kind of interesting. That is actually very interesting. It's not what I would expect, actually, because I'm actually quite, I think I know why. So what actually happens there, and it kind of is related to this question in the challenge, or wait, no, it's related to the question number 2 here. So what's going to happen if you actually try to run this program? So first off, the user space program tries to trigger interrupt 14. So first off, in the OS, we have not even configured interrupt 14 in any way yet. All we support is interrupt 0. So right off the bat, that immediately is not going to work. What I'm actually going to do right now is just add support for probably one of the most important traps, which is the general protection fault, which is number 13, and you'll see why in a little bit. Protection fault. T G. Okay. How do I get to my constants? It's TGP fault. GP fault. And so now I've declared and registered the stub, and now what I need to do is set up the IDT entry, which I'll do right here. And protection fault. That's what it's called, right? General protection fault. And why is it highlighting this in a strange way? Does it build? It doesn't build. Why not? Oh, because I need to add, it's like this, I need to add a function prototype for this assembly label. There we go, entrap.h. Oops. All right, what are my registers? I copied this somewhere. Damn, do I really not have it? I need to copy this again. That's kind of annoying. All right, general, does it cut? Okay. So I need to declare the, is there a similar warning resource for ARM-based OS dev? The only thing that I know of is the OS dev wiki, which I believe has an ARM section. I'm not aware of like a college class like this, which does an OS with ARM. Yeah, I'm not totally sure. Okay, so now we have our function prototype. And I'm just initializing it in the exact same way as previously, just to re-explain this macro. So the first thing you pass in is the IDT descriptor, like the interrupt gate structure, basically, as we've defined in the IDT. It's like this specific type. And then you pass in these four things. You pass in whether it is a trap handler or an interrupt handler. This kind of goes back to the question from earlier about what's the difference. And it explains it right here in a lot of words, is the effect on the interrupt flag. Something about resetting an interrupt that vectors through the interrupt gate resets the interrupt flag, preventing other interrupts from interfering. Right. A subsequent IRET restores IF to the value in the E flag's image. An interrupt through a trap gate does not change the interrupt flag, right? So you pass in whether it's a trap handler, and in this case, I believe both of them are. And why do I say that again? I think I said that because I think this diagram told me it says false, but also the manual has a very useful reference for all this stuff. If you go to section 6.15, you can see the interrupt reference. You know what? I'm not actually totally sure. I think maybe because it was a fault or something, it says fault there, but I'm actually not completely sure about that. But anyway, I was just putting one for for the trap, the is trap so far, which I believe is correct, but I'm not totally sure. Then you pass in the code segment selector for the handler, which is kind of interesting that it offers that, because we will always be handling interrupts in the kernel, and we only have one kernel segment, like text segment or like code segment, basically. So this is going to be the same for everything. Fourth one is this offset. So that's actually the function pointer. And yeah, that's just the value of the function pointer. And then lastly, it's the privilege level. And this is actually pretty important. This is the minimum privilege level required for software to invoke this handler explicitly using the int instruction. And so that's totally related to what we are doing right now. And so I'm putting these all at 0 so that that basically user space is not allowed to directly trigger these with an int instruction specifically. So I'm actually I think that might actually be it for everything I need to do. So I'm going to run this again. So as a refresher, we are running the soft int user space program, which triggers this int 14, and the 14 is not the same as 13, which is what I just implemented, but I believe what's going to happen is that the processor is going to see that 14 was attempted, but it's going to see that, well, actually, I guess there's no IDT entry for this one yet, so it might even reboot. Let's just see. No, it actually didn't fail. It actually did it hit the GP fault, I believe. That's why it says general protection fault. So what this trap frame is printing out is this trap frame text is just printing out the values in the trap frame, which is kind of cool. And we can see all these different things from top to bottom. Although actually we don't have all of the register value, or do we? We have EX. I guess we do actually. Yeah, we have all the register values. Then we have these two segment registers which we manually pushed in our all traps function, and we have all the CPU pushed stuff. Although this trap number was pushed by our assembly stub to NSD, which stands for general protection. So that's kind of interesting. So what happened is the interrupt 14 got converted into an like a trap 13, and I'm guessing it's because I think it's actually for a different reason than I kind of might think. So let's pretend we went one step further and actually implemented the page fault, like started handling the page fault interrupt, which I will just quickly do trap entry.s. So let's just, because I think it simplifies things a little bit, but time for a 20-second break.
That's what the map is for.
All right, I hope you stood up and stretched. Yeah, so let's walk through what happened there step by step. So I'm just going to simplify the things a little bit and page fault. Fault, I guess. I have to figure out how to name these better. Maybe I'll call it, maybe I'll prefix them all with handle, basically. Handle, I don't know, I'll figure that out later. Oops. So, now I want to yank this. I'm just thinking about if I can do this in a better way, but I can just yank that and paste it, because I will also need it above, not there. I'll also need it in right here, no. Where was that thing again? It's in, did I miss it? It's in trap.h, right? Are there two trap.h's? There are two trap.h files. That's so confusing. Okay, it's in this other trap.h. And I guess I'll just do this. So now we got that. I'm just gonna close all these random tabs that are open while I'm here. Okay, so now we're handling this, and we've actually advertised that yeah, it's also not allowed to be called from user space by putting this 0 here. So I think what we're actually going to see is kind of the same thing happen, but I think there's a few different reasons for that. So I think we're going to see the same thing happen again. It triggers a GP fault. But here's my understanding of why that happens. So user space is going to trigger the int14. The 14th interrupt, the page fault interrupt, advertises that user space is not allowed to call it. And therefore, it converts the trap into a GP fault. Yes, that's kind of what it's getting at this question. Soft int code says int 14, why should this produce interrupt vector 13? And just for fun, I'll just quickly see if we can find this in the manual. We're gonna need to look it up in, I guess, in the IDT descriptors, maybe. I do find this a little bit difficult to read. It's shadow stack stuff. Maybe it's documented in the, I was kind of already here, in the actual instruction, in the documentation for the int. Yeah, I think it was here or something. Yeah, it's right here. Each of the int, like int n, int, I guess maybe 0, and int 3 instructions generates a GP exception if the CPL, so the privilege level, is greater than the DPL value in the selected descriptor. I think CPL stands for basically the privilege level of the code that's currently executing on the processor, and the DPL value is that value we were seeing in the IDT that advertises what the what the privileges that are required to execute this entry via the int instruction. So I think that's where it's documented. That's where this conversion process is documented. So the 14th interrupt gets converted into a GP fault specifically because this handler does not permit it. And so one interesting experiment we can actually do is convert that to a 3 and see what happens. I don't like totally know, but I think we might actually see it say page faults here, because now user space is allowed to trigger page faults directly. Okay, that didn't work. It says general protection still. Which is interesting. I actually can't really explain that. So just to check page fault, it's number 14, right? So that's interesting. Oh wait, I have actually an idea. I forgot to update something. I forgot to update this to be page faults, and that's actually important. What this variable is, this variable corresponds to the variable that's pushed onto the stack as the interrupt number, and I think that's actually the source of that bug. So if I run it again, yeah, now it says page fault, and that's consistent with my understanding, because yeah, previously what happened was I had this bug where we were kind of, the page fault stub was incorrectly using the interrupt number for the general protection fault, which meant the C code later just is going to look at that number to see what happened, and it's just going to see this kind of wrong value, this GP fault value, and print GP fault. And so now that we've corrected that, what we can actually see is that so soft int again. We're triggering, user space is triggering the 14th interrupt. Our IDT has advertised the 14th interrupt as being like okay to be triggered from user space because of the 3. And so what happens is it actually goes fully through, and we're now handling a page fault directly triggered by user space actually. But while that's interesting to see, we don't want to keep it like that. This kind of gets into the question, they're asking, like, why should it produce 13? Like, what happens if the kernel actually allows this to invoke the kernel's page fault handler? So I don't really know a great answer, so I'll need to kind of figure it out, like just brainstorm in real time. But I can just, for one thing, the kernel in general wants to be very tight about what surface area it exposes to user space. And it, in general, doesn't allow permission except in very specific interfaces, like for example, the interrupt for a syscall or whatever. And so just as a matter of principle, since the kernel basically should block access from user space unless there's a specific reason, then it does that. And so that's a first reason. It's simply like the page fault interrupt is simply just not part of the API exposed to user space. And I think my camera's messed up again. Let me try to figure that out. Or I might just switch cameras back to yeah, I'm just gonna make my bed. All right. Yeah, so camera. All right, we're switching back to desktop camera today, because apparently my camera was frozen. All right. Let me just center it. There we go. Yeah, so where were we? So we were just talking about why it's important that the kernel block access. Also, that's just not supported. Yeah, why would we allow that? So it's kind of cool that we're seeing this. It worked, actually. It converts it into a 13, so that's good. And yeah, so just real quick. So before we had this set up, it actually still produced the GP fault. I think in this case, it actually did that because actually when this happened, it went to look up the privilege level of 14 in the IDT, which is not set up. So I think the processor actually generates like a fault when that happens, basically because like this thing was just simply not set up, but it had the same observable effect of the GP fault running, basically. And then now we kind of do a similar thing and we can set it back to 0. We're still going to see the GP fault, but the reason is different. The reason is because it triggers 14. The processor looks up 14 in the IDT. It sees that it exists, but the privilege level isn't high enough. And so then it triggers the GP fault for that reason. All right. I see. Oh, I was missing some of the chat, I guess. Oh man. I was like not scrolled in the chat all the way. Let me catch up on this a little bit. I would imagine a class like this would transfer over a lot of the skills to ARM. Yeah, it's probably true, I would say. I mean, a bunch of this is a little bit x86 specific, but also ARM is a lot simpler than x86. It doesn't, like, ARM doesn't have any of this kind of complicated descriptor, like segment stuff. Yeah, okay, camera seems frozen. Thanks for the heads up. Yeah, I'm using a Kinesis 2 Freestyle keyboard. What up, Plebish? Good to see you. High profile switches are hard on fingers. What's trapped? Is that another word for interrupt? Yeah, they're kind of similar. They're basically very similar things. They just differ with like the interrupt flag, which is like this really which is kind of an obscure detail, but yeah. And also, hey Ismail, what's up? Nice to see you. So we're going, this is going great. We're implementing a few more trap handlers, which is pretty easy now that we have the infrastructure working. And what I want to do now is go to bad segment. So the course is saying that we should be able to handle the bad segment something. And it also might be worth looking at these tests. Grade lab 3, for example. So I'm not really interesting. Grade lib. Maybe I can try to actually run these. What's grade lib? Grade lib is this Python from future import print function. Seems like Python 2. I kind of wonder if I could just run this with Python 3. I'm just gonna say, or I'll just type opt homebrew bin Python 3, or maybe it's or I think end Python 3. Python 3 will be good enough. Yeah, that's good enough. So just out of curiosity, what happens? Make a grade. Wow, it did something. Okay, that actually worked. That was kind of cool. Let me try that again. It like actually, it really is trying to run. Whoa, look at that. That's pretty cool. I'm running the grading script. Neat. And okay, a lot of things are not succeeding because I haven't done them. But yeah, right. That's awesome that it works even years, like 6 years later. Okay, that's cool. Can I stop it? Okay, I got a 10 out of 80, so I guess I have some work to go. Other? Yeah, whatever. So I'm just gonna scroll back up. So I passed. I guess it doesn't matter here. Yeah, I mean, I'm not doing this for a grade, but it's helpful to know if I actually have bugs that I'm not aware of. So that's why I would be interested in doing this. But let's see. So I'm apparently passing the div 0 test, but I am apparently failing the soft int test. And I kind of don't know why. So what does it say? Good. Incoming trap frame. So I guess I don't really know how to interpret this output. Oh, does it? Interesting. Does it Kimu output saved to this? Wait. Default read bad segment. Is there some way I can run only part A? That would be nice. But soft int. Right. Is that what I just did? Yeah. So maybe I can just only run this thing. Does that work? And only run one of the tests? Or that does not seem like it's working. Hello. All right, that did not seem like it worked. but it's not good that I'm not passing this test. Let me try to read the test to understand it. Soft int. I wonder, interesting. User test soft int match. Welcome to the JAWS kernel monitor. Incoming trap frame at. Apparently that was missing. Like all these, like a couple of these things were missing actually. So, So it seems like, all right, this is kind of, it would be nice to read both, but my thing is too small. Okay. Okay, let's close this. So, EFFBC, we're at B8. So I think it's complaining about that, missing trap frame at. And, oh, interesting. At hex F something. So that's also why, like, it's failing the test. Oh, because some very specific numbers. Oh, interesting. Actually, this looks kind of wrong. This looks actually wrong, but it's time for a 20-second break, so we'll be right back. It's too bad about the camera. Camera's not working, yeah, unfortunately. So now I'm back to the front-facing camera. Okay, so actually, oh wait, I think I know. I think I know. So there's a problem, and so this is actually a problem. It's EIP should be something 8 because that corresponds to the code that was being executed. But here it says EIP is 72, which is wrong. Yeah, like that's just simply wrong. And I think I know the reason why. I think it's because when I did this a bit too quickly, and I just was kind of blindly using this trap handler no EC thing, which means no error code. But I think some of these actually do push error codes. And that's just, yeah. And so, yeah, so basically that's, excuse me, that's the issue. Both 13 and 14 do push an error code. So I need to change it. I suspect the test might pass, or hopefully would. I think I'm doing things correctly, aside from that. But yeah, that's actually good that I ran the testing script then to learn about this. It would be great to somehow like not run all of them, but only run the ones I want. Grade lab 3, grade flags. What? I guess I just run the gradings. Can I just directly run the grading script? Can I run -H? I can, okay. -V, interesting. But it doesn't allow me, or maybe I can just look directly at this thing. run tests. Okay, it's not super descriptive in terms of what I can or can't do. So maybe I'll just hack it. Maybe I'll just comment out everything here, but end part A. Yeah, so what I'm going to do is just comment it out. That's the easiest way to only run the tests that I want. Let me do that. Make grade. All right, let's run it. Div 0. Okay. Soft int. Okay. Bad segment. This is gonna fail, I think. Okay, that succeeded. Okay. I don't know why that succeeded, but now I am passing the tests and going to get a good grade with this. So yeah. That's cool. Well, let's understand why I passed bad segment. Pog. Yeah, Pog is right. Yeah, I'm gonna call that a win. All right. Let's look at bad segment one more time. I never really understood this. So this comment says program to calls a GP exception. Try to load the kernel's TSS selector into the DS register, which is hex 28. Okay, that's such a strange thing to do. Try to load the kernel's TSS selector into the DS register. So like, first off, what does that even mean? Like, okay, let's break it down. So the DS register, first off. So the DS register is one of the CPU's segment registers. Stands for data segment, I believe. And the way these segment registers work is they basically contain indexes into the GDT, which is this data structure that the OS sets up. And basically I think there are a couple of details about some extra bits or whatever, but mostly they are indices into this table. And it's kind of like a pointer at like a segment. So they select one of these things. Okay, so that's what a DS register is. And normally you pass it things like the GDKT or the GDUT, like kernel text or kernel data or user data. I mean, for DS, it's specifically going to be these data segments. So usually you like set it to the GDKD thing or GDUD. What this is trying to do is move the TSS selector. And so the TSS is another entry in the GDT, but it's kind of like a system entry. It's not like a normal descriptor. The normal descriptors set up memory segments, but the TSS is a different kind of system data structure. So it doesn't make sense to load this index into the DS thing. It only makes sense to load these quote unquote normal segment descriptors into DS. And yeah, so that's like the base understanding of what is happening there. And then so now it's like now user space is trying to load into DS. I actually don't totally know what happens there. I'm assuming that this action produces a GP fault. We can observe this. Let's take a look. Please just, okay. So we can break on we can go to bad segment and we can find the instruction that does this, I hope, maybe? Where is main again? Umain. Oh, umain is right here. Yeah, so here is the instruction. So we can break on that instruction and continue. All right, what happened? Did I copy that? Oh, okay, okay. I forgot to update this with bad segment. So what is umain? Umain is it's just the main function for, like, yeah, it's just called umain. I don't really know why, but it's just it's like the normal main function for user space C programs in this OS system for some reason. It's just called umain instead of main. Yeah, nothing really too special. Yo, professor. Yeah. Sorry to ignore you. I just don't know the answer to your question. What skill is the best for future like data analytics, machine learning? That's a bit too broad of a question for me to really answer. And here I'm mostly interested in systems programming. So I'm at a high bias of telling you to study systems programming, which may or may not be good advice for you. Yeah, so I was basically just not running the right program, so let me redo that. All right, rerun it, attach the debugger, and continue. And now here we are. We are at the move instruction. Well, technically this is allowed. So this is all this is doing is moving some number into the AX register, and AX is just a general purpose register. So this should work. What might not work is what's next, though, because now we are trying to load the 28 into DS. And I guess what is going to happen there is when you try to do that, the processor probably reacts to that by it sees that, okay, you've now changed this DS value. So now let me use that value and look up the new segment descriptor to use. And it probably needs to reset a bunch of CPU internal state when you do that. But in this case, TSS, just first off, is not like a selector you can use with DS. Forget the fact that it's not even a user space thing at all. So my guess is that, yeah, somehow moving an invalid value into DS is another reason, or another instance where GP faults are triggered. Let me just test this. So step I, my prediction is that this is going to cause the GP fault. Yep, and here we are, we're in the GP fault handler. And we could probably look that up somewhere in the manual. I don't have a good idea exactly where. It would probably be in the documentation for the segment registers, maybe, or maybe the move instruction, I don't really know. But that explains why the tests pass, I guess, just because I don't know, because we have the GP fault handler set up, and so we're going to be ready to receive that if it happens, basically. So yeah. All right, but it looks like I am actually kind of finished with this assignment. Let me just run the grading script again just to watch that succeed, because that was kind of cool. Div 0, okay. Soft int, okay. Bad segment, okay. 30 out of 30, nice. And if we go back to the page, yeah, we're passing that. So we've successfully finished exercise 4. And maybe I will commit that. We good, yeah. Maybe I'll just take a moment. Okay, I'm just going to take a moment to clean a little bit of, and I'll actually just go into fork because it's a little bit easier. So don't need this. Don't need any of this. We do want this. I do want this. Don't necessarily need this. And I actually do want this. It's a bit of a separate change. But for the moment, I'm just going to quickly do some better naming on these handlers because they are poorly named right now. I think there should be some kind of consistent naming. So first off, error is not the right word because it's technically an exception. Maybe I can find something in the manual. Like maybe I can use some of these really like official names. Divide error exception. Is there a list? I thought there was like a big list here somewhere. Or yeah, I think it was towards the top here. Yeah. Oh, I guess that's why I called it divide. Why I called it divide error. That's what it. That's what it says. So it's divide error. General production. Page fault. Handle. So, but yeah, those are the descriptions. So there's some kind of easy name I can copy. Divide error exception. Okay, and this is like kind of slow. Stack fault. General protection exception. Page fault exception. I'm going to use these very official names. So I'm going to call it handle divide error exception, or yeah, handle was a page fault exception, general protection exception. It's a little bit of a like long name, but divide error exception. So, or I could just do handle divide error, handle general protection. Maybe that's enough. Handle general protection. I think I like that a little bit better. The redundant exception everywhere is trap.h. Is it in the kernels one? Yeah, it is. Or no, wait. How? Where? I'm always getting... Is there trap.h, right? Divide error. Oh, it's... Okay, I was just moving a bit too fast. So... Yes, man, did you start learning to use Git at uni or later when working? A little bit of both. I got exposure to it in uni, but in just kind of a like basic way. I think in like just like the pure basics of like kind of some branching and commits and stuff. But I only really started to learn it when I started working though. And in particular at my current job, we use Git pretty heavily to do rebasing and stuff like that. So it was a lot on the job actually. Okay, doing some copy and pasting. And now the last place to do that is here. Handle page fault. And okay, now the cool part about having the grading scripts working is that I can just run them again and make sure, hopefully, that they still pass, please. No, are you kidding me? Oh, whoops, somehow my panic got inserted back. That's why it failed. Okay, please work. Okay. Yeah, what's up, funny step, BK? It's been 2 weeks since I began learning C and C++. Been quite a ride, but I haven't made anything yet, actually. I don't really know what to make. Yeah, good question. So I can just tell you what I made. When I was trying to learn C, so first off, I was using this book called Learn C the Hard Way, but what I wanted to do was actually use C to make like an HTTP request to like a web API, because I was coming from that background. And for me, that involved learning libcurl to make HTTP requests. And that was actually a pretty instructive experience. And you can even see what I tried to do here on my GitHub. It's like this lib requests thing. So if you don't have any ideas, that's kind of what I did. And I learned a lot through doing that, through using libcurl and just make some HTTP requests and stuff like that. Yeah. Okay. So it looks like this worked, which is good. And the reason why I kind of staged stuff is just so I can see the diff more cleanly. But it's time for another 20-second break. Be right back. This thing, and yeah. Oh yeah, another idea for a project you can work on is writing a shell, like your own version of Bash or something like that. That's a pretty instructive project to work on, and you learn a lot about like forking processes and file descriptors and stuff like this. So I actually write shells whenever I learn a new language, just because it's a pretty good project. It involves input and output, it involves string parsing, it involves some making specific syscalls and stuff. So yeah, interesting to see how you use Git. Like my usage is so messy. Yeah, I mean, yeah, like definitely it's you can learn a bare minimum of Git and do a bunch of stuff, but you can also and yeah, unless you have been exposed to kind of different ways of working with Git, it's kind of hard to I guess basically like kind of have the effort to move to the next level of working with it. But yeah, that's just kind of how I do it. So I've kind of done something a little bit bad and done the rename at the same time that I added all these new ones. I'm just going to amend it all into the first one. And this is just changing the program we're running. Doesn't need to really be committed. Yeah, I think I'll also just amend this one in there too. This, I need to, yeah, make div 0 program actually do divide by 0. Okay. And we have my little local change. I'm going to commit this to make lab 3 grading script work. Yeah, making your own shell tells you a lot about whatever language you're learning. Yeah, totally true. Yeah, just for fun, I'll do a bit of a show and tell and show you a shell I wrote 9 years ago when I was trying to learn Rust. And that was the last time I ever did any Rust programming. And I called it Relish for whatever reason. And it was just one file, and I basically didn't do very much. It's like it is like this really bad shell that I wrote in 300 lines of Rust. And yeah, that was like interesting. So that was the last time I wrote Rust. Okay. So now we're ready to move on to part B, which is kind of pretty exciting. Let's do that. So what does it say? Now that your kernel has basic exception handling capabilities, you'll refine it with more important primitives. Page fault exception is particularly important. When it takes a page fault, it stores the virtual address that caused the fault in CR2. In trap.c, we have provided the beginnings of a function. Okay, exercise 5. Modify trap dispatch to dispatch page fault exceptions to page fault handler. Oh, is that it? You should now be able to get make grade to succeed on the fault read kernel, fault write kernel tests. If they don't work, fix them. You can boot JAWS into a particular using program using make run x. Actually, that would be very useful. I want to learn how to do that actually. Can I just do that? For example, so are you telling me that this works? Holy crap, I think that worked. Wow. And it failed because we don't implement like syscalls or anything like that. But if I do the divs, is this how it works? No, Knox. Divide error. That is wild. That is so cool. And if I do the soft int, it triggers the GP exception. Yeah, that is so useful. That's actually a game changer because it means I don't need to carry around all of these changes anymore just to change the program that I'm running actually as the init program. Hey Vignesh, currently working on a password manager, trying to implement encryption. It's like writing C. Nice. I mean, that's a pretty ambitious project, but cool to work with cryptography and I guess OpenSSL maybe if that's what you're using. So, yeah, I think that's good idea for a project. All right. So let me do this. Modify trap dispatch. So how would I do this? So specifically, I'm trying to dispatch the page fault exception. And trap number. No. So I'm just gonna get the trap number as a variable, and maybe I can switch. Wow, that generated a lot of stuff. T page fault trap hand or what is it, page fault handler, and I probably need to pass this thing in, maybe even return. I actually don't really know. Default break, that's my guess actually. Yeah, maybe not necessary to make a variable just for that one thing, but yeah. So I'm just gonna just gonna do this. And yeah, so now we are starting to execute this function. Read CR2. Is that it? Or like what happens? So let's go to the grading script. So now I'm graduating to all of these fault things. And we should see some stuff. Yo, what's up, devoid dude? Hello, friends. Hello. I read blah, 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 blah from location 0. Let's just give that a try. All right, I'm gonna uncomment these. I'm going to comment out these. And I don't know, let's give it a try. Make grade. Okay. Is that C or C++? That is C for now. Yeah, eventually I would like to get to C++, but so far I'm just keeping it very simple. And okay, somehow that was super easy and that just worked, so okay. So apparently all I needed to do to make that pass was literally just dispatch based on the trap number and call the C function. And the grading script just checks that it says some stuff like this, like page fault and something here. I wonder what this no thing is. Huh. I don't really know. Yeah, started my journey learning C recently, background in Java. I like C so far. Nice. I think Java is a cool language too. I think Java is super useful. Like lots of lots of major parts of the world run on Java. Like I think people make fun of it or whatever, but I think that's a cool language too. But yeah, C is very useful to know if you want to really understand how computers work. So I guess that was easy. Okay, nice. That was like the fastest exercise I've ever done. Okay. I don't quite know. I'm just gonna say dispatch to page fault handler. Some of these exercises take me like 2 months, some like 5 minutes. That's funny. The breakpoint exception. Ooh. Okay. Interrupt 3 is normally used to allow debuggers to insert breakpoints in a program's code by temporarily replacing the relevant instruction with a special 1 byte int3 instruction. So yeah. So normally these int instructions that allow you to trigger arbitrary interrupt numbers are, I think that's a 2 byte instruction, but it's useful to have a single 1 byte instruction for doing this kind of stuff, which is why they special case the third interrupt and make a special instruction that just does only interrupt number 3 in 1 byte. We use this exception to turn it into a primitive pseudo-syscall that any environment can use to invoke the kernel monitor. The user mode performs an in3 after displaying its panic message. Okay. Modify it to make breakpoint exceptions invoke the kernel monitor. Also, I skipped this challenge above. You should probably love between the lists of trap handler and their installation in trap.c. Clean this up. Change the macros to automatically generate a table for trap.c to use. Interesting. Now you can switch between laying down code and data by using the directives.text and data. That's kind of interesting. I don't feel that motivated to actually work on that. And I'm not going to do that. All right. But what I will do is work on this exciting breakpoint exception task, which sounds super fun now that I kind of am more confident with this stuff. So, okay, so step 1 is to not make the same mistake as last time and actually look up whether breakpoint has an error code, which it doesn't. So that means we can do this. And I'm going to call it the official name to be like a really good namer breakpoint exception. Handle breakpoint t break. Okay. Trap.h. Hopefully one of these has it. Trap.h. Burke Pete. Okay, that's what it is. Burke PT. But yeah, this is getting a little bit tedious. Oh no, what? Half of programming is naming stuff. That is so true. And I'm just wondering why this thing I yanked is not in any register. Okay, I'm going to try to be better. I'm gonna yank it into what, like the Q register? Let me try that one more time. So if I do, it's like quote Q was it I'm totally blanking on the vim command to use. How do you select? So VIW selects the word, right? So if I do quote Q VIW, that should be in my like Q register. I did that wrong, I think. That annoys me so much. How to yank into register. I always forget how to do that. It's all you do is prepend the increment with register name. So it's just Q VIW Q VIW P. No, I'm trying to yank on VIW. Oh, okay. Q VIW yank. And now if I look in the registers, it's still not there. Are you kidding me? All right, I'm not gonna stop until I get this right. All right. This is crazy. How do I do this? Copy. Yeah. Okay. If you want to copy the current line, so you do need this thing. All right. Once more. Quote Q VIW yank registers. There we go. Okay, good. For some reason that thing was getting clobbered everywhere. So now I can just do Q paste. And I can also go to, oops, I can go a bit down. And I can do VE control capital P. Oh, wait, what? Ah, no, okay, VE quote Q capital P. Ah, okay, but no, so I just wanted VIW capital P. No, VIW quote Q P. All right, nice. So now we're handling the breakpoint exception. Yo, what's up, useless? Any starting point for OS dev? I mean, yeah, like, I think if you're the limine bootloader OS dev, I mean, that's probably as good as any. Personally, I'm a big fan of this MIT course. I think honestly, that's been my personal, like, the best thing that I could have done to start learning this stuff. And I've learned a ton, so, but I need to be careful to do this correctly. So, yeah. Okay, so get rid of these Vim tabs. So now I need to make, all right, so first off, I'm just going to run the, I think there is an int3 or like user like int or like user breakpoints. I'm just gonna run breakpoint Knox. Yeah. Okay, that's interesting. Why did it say oh, I think I made the same mistake as last time. No, did I not? No. It's properly doing the breakpoint thing here. So why would it be triggering a GP fault? Now that is actually interesting. I'm setting the, so there's like 3 parts to setting up a new handler. You need to declare the assembly stub. You need to make the prototype available, and you need to set the interrupt gate, the gate descriptor. Ah, but that's why. It's because I disallowed user space access to that interrupt, but that's actually not true. In this case, I actually genuinely do want to allow user space to do int3s actually. So that's why. That's interesting. So let me run that again. And here we go, breakpoint. So that is working. That's pretty cool. I'm gonna reset this thing a little bit. Get rid of this pain. Oh no, oops. Wow, what happened? Okay. All right, 20-second break, be right back. I just got rid of a pain that I kind of wanted. That's too bad. All right, give me 1 second while I refigure this out. Okay, back here. Make or what was it? Is that not right? Oh, oops. I'm just in the wrong directory. Okay, make run breakpoint Knox. Ah, what was all this stuff? Nothing to be done for warn. Interesting. Usage. Okay. Some command is not running successfully. But anyway, okay, so we're back in action. And now it's time to go to trap dispatch. and add a handler, and I'm going to call it, I'm going to diverge from the naming. But I already have this thing called handle. Yeah, I already have this other thing called handle breakpoint, but it's all capital and whatever. So I'm just gonna name it, I'm just gonna name it handle breakpoint, and I can rename it later. Yo, Pingu XOR, what's up? Handle, so I'm just gonna copy this and handle breakpoint. What's your best advice to get into low-level exploitation? Definitely pwn.college. That is easily the best resource on the internet in 2024 for that kind of thing. Yeah, I wish I had that when I was learning that stuff. Okay, let's run it and see. Oh, I need to. Do I need to declare? There's probably a header file. That's why it's kind of annoying that I need to do that, even though this is like a private function. You know what? I kind of just, I'm going to, well, maybe I'll do that after. Realistically, this should just be below all the other files, I think. Like I don't want to add a prototype in our header for a private function to this translation unit. That doesn't make any sense. So in the, yeah, I don't know. I could just add it above here. What to do. All right, here's what I'm going to do, I think. At a small risk of messing up a little bit of my Git and whatever, I am actually just going to stash things. Then take this opportunity to, oh man. Okay, take the opportunity to move this thing like all the way to the bottom, basically, which I'll do as a separate commit. Move trap dispatch to the bottom, and then I will pop the stash and fix this merge conflict, which I just created for myself. Or it'll probably be pretty easy though. Okay. So I just want, so this thing's at the bottom. So here it's saying like, it's saying in the version of the code that we're trying to like apply here, it had all this code here. In the parent commit of that, it had the same thing, but in the current world, there's nothing there, and it doesn't know what to do, and we would just want there to be nothing there, so I'll just accept the current change. And the consequence of that is now handle breakpoint, which I guess could be static also. The consequence is that handle breakpoint should no longer need a prototype, because it is just simply before, although strangely, something happened to my case statement. So, but handle breakpoints. But now this should actually compile. Make. Was it? Oh no. But I have a syntax error, I think. Handle breakpoints. Yeah. But that. Implicit declaration of trap dispatch. Oh no. Trap dispatch. So now this trap dispatch thing is. Oh man, it's so annoying. I'm just going to. Okay, I'm going to stop caring about this so much and just quickly add like a little thing at the top to not get blocked anymore by this. Interesting. Okay, so now it compiles. How to learn assembly. So I think pwn.college has a bunch of stuff about that. I would probably just recommend doing some reverse engineering tutorials and like challenges and stuff like that. That's my advice on that one. Okay, so now we're compiling. So now let's actually run this breakpoint thing. And I think it worked. So it hit our panic. Okay, so it hit the panic, so that's a good sign. And what do I actually do though? To make breakpoint exceptions, invoke the kernel monitor. Okay, cool. And the way I do that is I think there's a function called monitor. Yeah, which you can call and pass in a trap frame. I think the idiom was like while one tf. Okay, let's try that again. So, interesting. Okay, so I was just wondering why it printed this whole trap frame thing, because that is typically what's printed if we were handling an unrecognized interrupt. But I think monitor prints it out. Yeah, monitor prints it out too. So that's why. And also says welcome to the kernel monitor. So I think that's working. Yo, hey, Nirajan. Nice to see you. So if I run the grade script, and just out of curiosity, what does it look like these days? So, okay, so now I want to run only this one. So I'm going to comment out all of these. So now it only runs a test breakpoint. Please work. Nice, okay. And that's passing too, which is good news. Interesting. So what's all this stuff? Yeah, so this is all, I guess this is all the stuff that was stashed or something. Yo, TBA later. Hello, debugger. Hello. What application do you use in the terminal? This is iterm2. This is a lazy git for git. And this is fish shell also. This thing here is NNN, but I have an alias to just N. It's like this really nice file system navigator kind of tool, like interactive. But okay, breakpoint. So I did not want a few things. I don't want that. I don't want that. I do want this. I do want this. Okay, just gonna do handle breakpoint exception. Nice. Challenge, modify the kernel monitor so you can continue execution from the current location. After the int3. And so you can single step one instruction at a time. You will need to understand certain bits of the eFlags register in order to implement single stepping. And so, okay, so you can continue execution. And so are those two different things? Is continuing execution like different from single stepping? Like, yeah, I think so. Actually, I'm not totally sure how to do that. I mean, the obvious, like the first idea that just comes to me is actually kind of pretending to be like a debugger and like inserting int3 instructions like step by step, but that sounds kind of involved. So maybe there's a better way to do that. Yeah, okay, I don't really eFlags implement single stepping. Maybe like the other idea that comes to mind is maybe the hardware debug registers can be used to do that a little bit more easily. So I don't actually know really how to do that quite now. If you're feeling really adventurous, find some disassembler source code and extend the monitor to disassemble instructions as you step through them. All right, I think I'm not going to do this right now. Questions. The breakpoint test case will either generate a breakpoint exception or GP fault, depending on how you initialized the entry in the IDT. Why? So we ran into this. It's because of that bit that lets you control what's the minimum privilege level needed for the interrupts. Yeah. So that's why. And so if you don't set it to 3, then yeah, it's going to cause a GP fault. But if you set it to 3, then it will allow the interrupt. Okay, and then what do you think the point of the mechanisms is? Okay, I think just basically, yeah, allowing the kernel to control itself more. So control the interface from user space. Yeah, and that's pretty much it. All right, I think it was a pretty good one. It's 6, so I think I'll probably sign off now, but that was cool. That was a good stream. Got 2 exercises finished, 4 and 5. So yeah, good progress. And next time we'll begin, and 6. So next time we'll pick up where we left off with system calls, which should be very exciting. So I'm just going to link to my Discord. Like I do, feel free to join if you want to keep in touch. Like, comment, and subscribe, and I'll see you next time. All right, peace, bye.